Hello, my name is Kilian Olen, and I'm a rising senior at Embry-Riddle Aeronautical University, where I'm pursuing dual degrees in aerospace engineering and engineering physics. This summer, I had the pleasure of participating in the Robotics Institute Summer Scholars Program at Carnegie Mellon University, where I was tasked with working in the Air Lab on the GoAERO competition. Here's my presentation for my work over the summer, where I explore emergency response ambulance drones, and specifically with feasibility design for the GoAERO challenge. Now, the motivation for this challenge is that we are seeing more and more disasters worldwide. And now, while this is mainly attributed to improved report methods, these report methods have also highlighted some of the disparities that we have in emergency response. So in the US alone, you have nearly 4.5 million people that live in what is considered an ambulance desert. Now, an ambulance desert means that they have to wait at least 25 minutes or more for emergency crew to arrive. And in moments where every minute counts, this is extremely devastating. Now, the surprising fact is that only about 52% of these people that reside in ambulance deserts also reside in rural communities. So while you would normally think that rural communities would have a higher proportion of people that don't have access to ambulance deserts, this is also affecting people in all different scopes of communities. Even worsened is on the right, you see the FEMA Natural Risk Index, which uses historical data on natural disasters to determine how at-risk communities are. And it shows a concerning overlap with some of these ambulance deserts, most notably in the coastal areas and near the mountainous and rural areas near the Washington's Appalachians. So what exactly is the GoAERO competition? Essentially, it's a sponsored competition by several companies, including Boeing, NASA, AIAA, and several others, with the specific goal of developing a compact, semi-autonomous, electric vertical takeoff and landing ambulance drone. Now, this drone is going to be evaluated through three simulated missions, which are productivity mission, where you demonstrate the ability to quickly deploy a system and continuously ferry payload, which lasts approximately 90 minutes total. You have the adversity mission, where you have to demonstrate the ability to take off and land in difficult conditions. This lasts 30 minutes in total. And you have the maneuver mission, where you demonstrate the ability to tightly maneuver while avoiding obstacles, which lasts 20 minutes. All three of these missions are used to simulate real-world environments and determine how capable the team's design is going to be in a real-world environment. Now, as for my contributions for this project, this is the initiation of the 3-year GoAERO competition. So my project involves particularly preliminary design and feasibility analysis. I identified the governance design parameters from the GoAERO competition to see what is our limitations and how can we design a ambulance drone that matches the parameters that we need. I also explored preliminary design for aircraft sizing and mass estimations, and I analyzed the power to weight ratios to determine if current commercially available batteries are feasible to actually design a fully electric design. Because with the unpredictability of emergency response, you want to make sure that your system has multiple redundancies in place so your response team doesn't also become another emergency. Now for the sizing, the first mission of the GoAERO competition involves the transport and deployment of your aircraft on a truck, on the back of a truck bed of a standard trailer. In order to optimize transportation and storage, we decided to make our drone within limits of a road legal design, which means that it needs a maximum width of 2.6 meters or 8.5 feet, as you see on the figure on the right, which is the US highway maximum legal width limit for Pennsylvania. Now, the maximum length actually varies from state to state. However, we wanted our design to actually fit and on a standard trailer, so we decided to limit our length to 3.6 meters. And the height is also something that varies. We wanted to fit in a standard garage environment, so we limited it to 2.3 meters. Now, in regards to the mass, after considering the different types of motors and drive systems and also structural systems that we were planning to implement, or at least estimated the mass that we want to implement, we estimated that a design of this ambulance drone would roughly have a mass of about 400 kilograms, and we rounded it up to 451 kilograms, which is around 1,000 pounds, in order to account for any additional accessories and computing powers. Now, we compared the different mass and saw how it affected the hover times and also the additional parameters for the aircraft. And as you would expect, the heavier you make your aircraft, the more strained the system is overall. However, with our base estimate of an empty aircraft with zero payload at 450 kilograms, we see we have a maximum hover time of 11 minutes. And if you remember back to the prior slide, the lowest mission time was 20 minutes. And if your aircraft can only hover for 11 minutes, let alone maneuver or perform different height changes, then we do not believe that this aircraft actually has a possibility of being implemented in emergency response situations. We considered the hover time, the maximum payload that we could add, and it still fly, the tilt angle, maximum speed, range, climb rate, and also a rotor failure redundancy. So we opted for a 12 rotor configuration as opposed to an 8 rotor configuration, not only because an 8 rotor configuration displayed a lower hover time compared to 12 rotor configuration, but it also displayed less redundancy in case a rotor failed. So as you can see, as you go up to 450 kilograms, if a rotor fails, you still have redundancy in place where you're still able to safely control aircraft. However, once you reach 500 kilograms, we encountered that the rotor failure meant that it was not able to adequately control the aircraft in a safe manner. So while you could still safely descend, it does not recommend to actually fly the aircraft. Now, in terms of the power, as we mentioned earlier, if you can't even fly for 11 minutes and 450 kilogram empty mass without payload, then that doesn't really display a promising solution. And here is one of the range estimates and time estimates for one of our analyzed configurations. And as you can see on the left, we have a maximum hover time of roughly 14.6 minutes at hover. As you start to increase the airspeed of the aircraft, you can see that the time in flight starts to decrease as you would expect to draw on more power. And the range is only about over 1,000 meters, which is less than a kilometer. Now, this doesn't look promising for our current design, which is why while we believe that ambulance drones offer a promising solution for emergency response situations, as they can access more constrained areas than a traditional medevac helicopter and plane, further advancements in battery energy density need to occur before a fully electric solution can be made viable for the GoAERO challenge. Now, because of this, we seek to identify hybrid power sources such as gas generators and turbines or fuel cells that can sufficiently extend drone operating times to match the needs of the GoAERO competition. As the focus on a hybrid power source is so it can still capitalize on advancements in battery energy density. So once we have a sufficient weight to power ratio that we can transform our system fully electric, while still, whereas our hybrid design can still capitalize on battery improvements as well. We also seek to finalize our design considerations throughout the proposal for the GoAERO competition for this first stage of the competition. And after that, we plan to begin preparations for the development of a scale model to more accurately determine our characteristics of the aircraft. Now, I'd like to make acknowledgments that this work is supported by the NSF Foundation and sponsored by the Air Lab, which is the lab I was working in through the Robotics and Systems Scholars Program. I would like to personally thank Stephen Willits and the entire Air Lab for their invaluable guidance throughout this process, as it's really helped me grow, and as well as Rachel Burson and Dr. John Dolan for their continued efforts in supporting the RIS program, as I've learned much more about graduate school than I could ever consider. Thank you.